Okay, so I'm going to talk about the capacitance depends on what lab. This is page 5. Um, so, if you need help with the lab, hopefully I can kind of make it make sense to you. So, basically, the key idea with this lab is that, let's say you have this capacitor. I drew out 3 capacitors, and you'll see why in a second. Like, these are the 2 different ways capacitance is affected. But, if you just take your good old capacitor, right, just any old capacitor, and you try to vary the voltage, right? So if we have Q and then V, hopefully you understand at this point that it would be a linear graph, right? So twice the voltage means twice the charge. So the question remains, like, why doesn't the voltage affect the capacitance? Because if you have more voltage, that should lead to more charge on the plate. Doesn't that mean more capacitance? And although and I think the reasoning with this is what I used to think. The reason with that is because capacitance really means the capacity to hold charge. So it makes sense. Like, hey, if you double the voltage, you get double the charge. Shouldn't that mean like double the capacitance? But capacitance is not how much charge it can hold, right? If I can take any capacitor I wanted, crank the voltage up to like 10 million volts, and I can get like as much charge as I want. But that's not what capacitance is saying. Capacitance is saying how much charge can you hold for a certain voltage. So let's say I have 2 capacitors, right? And I'm expanding on that idea. But if you had 2 capacitors, and let's say this one had way more capacitance, like 10, 10 farads, whatever. Usually you don't see like 10 farads. That's a really big capacitance. Usually it's in like microfarads, but whatever, I'll say 10 microfarads, right? So this one has way more capacitance. What that means is, if I were to graph this guy's Q versus V graph, I would get a steeper slope. What does that mean? Well, if I were to take a certain point, so let's say like right here, we'll call this voltage 10 volts, I don't know. But this guy's charge being held is much smaller at 10 volts compared to the capacitor B's charge, right? So at 10 volts, this thing has more capacitance because it can hold more charge at 10 volts. Or like, for example, at 20 volts, it's going to hold more charge, right? Because theoretically, like, what I could do is I could say, well, if this is 10 volts, I can make this 1,000 volts. Now, this will probably hold more charge, right? Because it's 1,000 volts. But that's not what capacitance is saying. It's like a apples to apples comparison. If you have the same voltage, which one holds more charge? That one has more capacitance. The amount to hold charge at a certain voltage. So, if you increase the voltage, that's not increasing the capacitance, right? Capacitance is Q over V. It's the slope of this graph. Slope is staying the same. So if I double the voltage, I get double the charge. That ratio for capacitance stays the same. So what actually affects the capacitance, right? So if voltage doesn't affect the capacitance, why does this 10 farad capacitor have more capacitance in the first place? What is causing that? That's the point of this lab. So really there are 2 things, 3-ish things. We're going to talk about that third thing probably later on in this unit, but I know the worksheet talks about it. There are kind of 3 things that affect the capacitance of a capacitor. So before I get to the equation, I should talk about conceptually those first 2 things. So here I have a capacitor, and then down to the bottom I have a capacitor with much bigger plates. Now, hopefully you can kind of probably guess that this thing is going to have more capacitance. Why? Because it has a bigger area, right? It can hold more charge. If these batteries right here, if they were 10 volts, you're going to imagine, yeah, this capacitor is going to get way more charge. And remember, right, capacitance is not sheerly about charge, it's about charge at a certain voltage. I can make this battery 1,000 volts. This capacitor is probably going to have a lot of charge, more charge than this guy. But if you're comparing capacitance, you have to go apples to apples. You have to have the same voltage. That's how you can like compare capacitance. So bigger plates leads to more charge simply because like the plates can hold more charge. Now, if we increase, let's say we increase the distance between the capacitor, how will that affect the capacitance? Well, this one is not as like easy to kind of wrap your head around. The big plate one is kind of makes sense because it's like bigger plate, more space to hold charge. For this one, you got to think about the electric field and the voltage. So in both cases, they're having the same voltage, right? Because we're going apples to apples. Same voltage, and we know that the electric field between parallel plates is equal to the potential difference over potential difference over the distance. So if this is D, right? So if we have the same voltage difference, right? Because it's 10 volts for both cases. This guy has a much bigger distance, so it's gonna. So if you think about the inverse proportionality, right? Like the more distance means less electric field. Well, how do you get electric field? Or how do you get less electric field? You have less charge on the plates. So hopefully that makes sense. Now that is how these physical properties affect the capacitance. Bigger plates leads to more capacitance. Bigger distance leads to less capacitance. And what am I forgetting? I was gonna say something. And then a smaller distance leads to more capacitance. Smaller plates leads to less capacitance. So it's really just the area and the distance and one other factor we'll talk about. So the equation for capacitance based off its physical properties is equal to C equals so I'll say kappa epsilon naught area or A over D, the distance. So if you remember with resistance, there was kind of like two equations for resistance. You had the Ohm's law version, which equals like resistance is equal to V over I. And you also had the resistivity equation where like R, I should really do it like this. R is equal to V over I. And then, and I'll say C is equal to Q over V. R is equal to rho L over A. So the thing about this equation right here, this equation is not saying the resistance is affected by the voltage, right? Doubling the voltage doesn't double your resistance because doubling the voltage really doubles the current. 2 times the voltage, 2 times the current, resistance stays the same. Same idea with this equation. Doubling the voltage doesn't mean you get half the capacitance, right? Double the voltage, you get double the charge, same capacitance. These two equations are just stating like a ratio. The resistance is like that ratio between voltage and current. It's a ratio between charge and voltage. It's just like a true fact. It's not really like saying R depends on this or C depends on this. Capacitance really does depend on the dielectric constant, which we'll talk about, and the area and the distance. Resistance really does depend on the resistivity and the length and the area. This equation shows how the resistance is affected by its physical properties. Same thing with this equation. So that's how you can draw some parallels there. So what do the variables in this equation mean? The K or kappa, whatever, I don't know. The K is a dielectric constant. So the dielectric, most capacitors have something in between them, some sort of insulator. It could be like wood or rubber, I don't know. Whatever they use, whatever materials capacitor makers use, there's gonna be stuff in the middle. If you don't have stuff in the middle, there's air in the middle, and that has a dielectric constant of 1. And what that means is that air is not making the capacitance bigger. If you add stuff like rubber in the middle, it usually has 6 as the constant. That is not that would make the capacitance bigger. Air doesn't, so you can kind of just ignore air. It doesn't affect the capacitance. But you have epsilon naught. Now this is a constant. This is actually 8.85. And here, let's do this. 0.85 times 10 to the negative 12. That's just a constant that is on your equation sheet. And area is the plate area. Hopefully that makes sense. And D is the distance of separation. So that is the equation. Now I could go over these kind of practice problems, but maybe, I don't know, I think it's kind of a waste of time because I feel like these problems are pretty straightforward. Use the equation, right? So plug in your numbers, solve for capacitance. Number 3 in analysis is some proportional reasoning. So just think about it, right? And the trick here is that radius, it's a circular capacitor, so the area is pi r squared. So I don't know, I wonder if that's squared and r is going to do anything. That's something you can try out. Number 4 I can talk about though. I think number 4 is important to know. So the dielectric, why does the dielectric affect the capacitance? Watch the YouTube video. I think the YouTube video they link isn't 100% explain this better than me. But the way I like to think about it is if you do put a dielectric, so if let me just make a capacitor here. So let me use my art skills. I got a B in art and design, by the way. So, you know, no, I don't know why that was important to share. I don't know why that really matters, but I'm not really. So, okay. If this is our little battery circuit capacitor thing, these are the two plates are like sandwiched, and they're sandwiching an insulator, and that's a dielectric is in between. So why is this going to affect the capacitance? Well, if I were to draw, and I shouldn't have shaded it in, I wanted to show, it's a dielectric. But if this thing has charges, right? And there's an electric field. So if this is a positive terminal of the battery, there's going to be positives on this plate, negatives on the other. Hey, it's going to create an electric field. If you have electric negatives on the bottom, positives on the top. It's going to create an electric field downwards. You can use E is equal to voltage over distance to figure out what that electric field is. But the dielectric, so if I were to like zoom in on the dielectric, it has its own charges. So if this is the top plate and this is the bottom plate, this is my dielectric, it has some charges. It's gonna polarize, but it's an insulator, so it's not gonna go like negatives up at the top, positive at the bottom. Instead, you're gonna get like a negative, positive, negative, positive, negative, positive. And it's going to polarize, right? So if the negatives are going to get closer to the positive plate. So you're going to get some polarization. And what actually happens is, you can think about it a couple ways. You can think of it as in like, there's now going to be an electric field, like a very small electric field caused by the dielectric. And it's going to point, so if you have positives and negatives, it's going to point upwards. And that electric field is kind of combating the electric field by the plates, right? So if you have an electric field downwards, the polarization is causing a small electric field upwards. And if we think about the equation, E equals voltage over distance. My voltage is the same because I have more, voltage is the same because I have the same battery. Distance is the same because same distance, right? Dielectric didn't change that actual separation distance. So my total, my net electric field has to stay the same between these parallel plates. So, if there's an upwards electric field, there needs to be a greater downwards electric field so that the net stays the same. Hence, you get more charge on the capacitor. Hence, the capacitance gets bigger. So watch the video. It'll definitely explain it better than me. I'm pretty sure Mr. Lindberger made it, and he's kind of my hero. So watch that video, and Mr. Gus, and all the physics teachers ever in the whole world. So yeah, thank you for watching, and hopefully this made sense. I don't know how to end these videos.